This is the lecture for Tuesday, October 30th. We will start by discussing center of mass, and then we'll talk about rotational motion, or actually review rotational motion, and then talk about moment of inertia. So let's begin with the center of mass. Okay, the motion, if you have a whole bunch of particles, the motion of a bunch of particles is very complicated, as you might expect. However, if you were to figure out the average position of all the particles together as one unit, let's say somewhere around here, some sort of central point, then the behavior of this center of mass actually follows the same laws of physics that we've been discussing for a point particle. Okay? So what I'm saying is, even though the behavior of a collection of particles is complicated, the behavior of the average position, what we call the center of mass, is actually very simple. And so let me just write this in words. The motion of the center of mass, and I'll define how we get the center of mass in a moment. The center of mass is just like a single point particle. With all the mass of all the particles put together, so with all the mass located at the center of mass position. Okay? So let me give you an example. Let's say we have two masses on the x-axis. Say one mass here, M1 at position x1, another one here at a position x2 with mass M2. And then let's say we get the center of mass of these two objects put together. Then, because this has more, seems to have more mass, the center of mass may be somewhere, something like this. Okay, so this has position xcm. So cm stands for center of mass. And the formula is that xcm, the center of mass, is equal to m1 times x1 plus m2 times x2 divided by m1 plus m2. Okay, so let me try to motivate why this formula works. So this is a bit like computing the average score for all the students on a test. Okay, so let me try to make this analogy. Let's suppose that we have, so the example I'm trying to make is the average score on a test. Okay. Let's suppose that M1 students get a score of x1. Okay. And let's say M2 students get a score of x2. And let's say these are the only possible scores. You know, let's say it was a test with one question, true or false. You get it right, you get 100%. You get it wrong, you get 0%. Okay? Then if I wanted to calculate the average score of all the students on this test, what I would do is I would add all the scores. Add all student scores. To add all the student scores, that will be equal to sum, okay, let's write this, the sum of all scores is equal to M1 students get a score of x1, and then we have M2 students get a score of x2. That will be the sum of all scores, M1 x1 plus M2 x2. And then what we need to do to get the average score in the test is divide by the number of students. and then divide by the number of students, the total number of students, which is just m1 plus m2. Okay, so then we get that the center of mass, or the average score on the test, will be m1 x1 plus m2 x2 divided by m1 plus m2. All right, so hopefully this formula makes some sense now. Now for the general case, of n objects, capital N objects, rather than just 2 objects, we have x center of mass will be equal to m1 x1 plus m2 x2 dot 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 to mn xn divided by m1 plus m2 dot 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 to mn. Okay. Now, if I call the sum of all the masses, if I define this as capital M total mass, then I can write this as xcm is equal to, and I'll use this sum notation. Hopefully this is familiar to you. The sum from I to I equals 1 to n of ni xi. That's just this numerator here. We can do this for the other coordinates as well. So for the y center of mass coordinate, it's 1 over the total mass times sum from I equals 1 to I equals n of mi yi. And of course for z you would get the same sort of thing. 1 over m sum from I equals 1 to I equals n of mi zi. Right? If I want to then put this all together, I can say my coordinates, my position, my center of mass position as a vector, it's xcm, ycm, zcm. This would then be written as 1 over m, the sum from I 1 to n of mi, ri as a vector. So where these guys are just the positions of each little piece, xi, comma yi, comma zi. Okay. All right, hopefully this is pretty straightforward. This is how we can calculate the center mass of a collection of particles. Now, if I have an extended, let's say I have an extended body, some continuous body, then rather than having a collection of particles, we have, so an extended body will be an integral rather than sum. So what we would have is, let's say we have some object like this that's made of some continuous material, and we wanted to get where is the center of mass. We would break it up into little pieces. And then for each little piece, you would have maybe some little mass dm here for the mass. And then we can figure out where the center of mass is, let's say maybe somewhere like this, rcm. And so instead of having a formula with summation like this, we would have an integral formula where it would be 1 over m, the integral, okay, of r dm, where we integrate over all the pieces. If you have any questions, please ask the student who's supervising today's lecture. Now, the next topic will be a review of rotational motion. So let's, you hopefully have this still very securely in your memories already, but let's review it. So review of rotational motion. I'll go kind of quickly. So let's think about an object going around a circle. this. It would not be there. Some angle here, some radius r, and it's going around a circle like this. Here's my x-axis, here's my y-axis, and let's say this arc length here, how long this segment is here. This arc length is what we'll call S. All right, now hopefully this is familiar. We talked about the average angular velocity. So we wrote omega ab or omega bar, and that's equal to the change in the angle over change in time. We have the instantaneous angular velocity, and this was just plain omega, that's theta dt. And so the units for this is radians per second. Now remember, radians is not a real unit like meters or kilograms or something, so in some formulas you'll see the radians will be omitted, but I'll write them here. And we also have the average angular acceleration, and this was alpha average AVG or alpha bar, and that was the change in the angular velocity divided by the change in time. And we have the instantaneous angular acceleration. That was plain alpha, and that was the time derivative of the angular velocity, omega, the instantaneous angular velocity. And so this had units of radians per second squared. Okay, I hope these are familiar. Now, we can make, we already did this, but we make a connection between the arc length and the radius and the angle. So if I have an angle theta here, it's a little too small, so maybe let's make it a little bit bigger. Let's make the drawing a little bit bigger. In fact, let's call it delta theta. And this is the radius r. And then this arc length here, how long this segment, this arc of the circle is we call delta s. And there's a very simple formula that delta s is equal to r times delta theta, where this is measured in radians, not degrees. Okay? And then by making this connection, we can then figure out that if we have a particle going around a circle with the speed v, let's say uniform circular motion, radius is r, then the linear speed v is equal to r times omega. Okay? So this is the linear speed, r is the radius, omega is the angular velocity. Okay, so if you want to be strict about it, you can say the magnitude of angular velocity. We're not worried about minus signs here. Okay, so we know that if the linear speed, if v is constant, we call this uniform circular motion. And we get the centripetal acceleration. Okay, so we have here's v. And then we have this acceleration a, r going in this direction, and pointing towards the center of the circle, and AR was v squared over r. This is centripetal acceleration. Okay, now if v is changing with time, then we also have, then there is tangential acceleration also. Here we call it AT, and that's going to be dv dt or delta v over delta t. Okay. All right. So let's draw two cases. If it's speeding up, then what we have is, first of all, we have AR pointing in like this. Let's say V is going in this direction. Then AT, if it's speeding up, is also going in this direction. Just like an accelerating object, the acceleration goes, if it's moving in a straight line, the acceleration points in the same direction as the velocity if it's speeding up. But if it's slowing down, in that case, it goes in the opposite direction. So when it's slowing down, v looks like this, but the tangential acceleration is pointing in the opposite direction. The radial component is pointing inwards towards the center of the circle again. Okay, so I should mention that AT, the tangential acceleration, is what we call AT, is simply related to the angular acceleration. And the formula is AT is just simply the radius times the angular acceleration. Now, suppose I wanted to write another formula for the centripetal acceleration. Let's write another formula for the centripetal acceleration, the radial component, this guy here. That's AR, we said it's v squared over r, but since v is equal to r times omega, okay, that's what we had just before, v equals r times omega. We can plug this in here for v, and we have that AR, the centripetal acceleration, is r times omega squared over r, and that comes out to r omega squared. So that's the formula for the centripetal acceleration in terms of the radius and the angular velocity. Okay, now we can talk about how something rolls. All right, so when a wheel rolls without slipping, this is what's going on. We have, let's say, let's paint something on. Think of a wheel. Let's paint something on the wheel here to mark out how it's rotating as it rolls along. Okay, so now I have the wheel at a later time. Okay, and let's imagine that there's paint on this surface here, and so as the wheel rolls on this paint, you'll notice that it will actually get paint on some section of the wheel rim. Okay? have the same length. And so let's say it's this much. And measure this angle theta. Okay. So this distance here, S, is the same distance as this distance here, S. Right? So we can make a connection between how fast the wheel is moving, how fast the center of mass, this is the center of mass, how fast the center of mass is moving, and how fast the wheel is rotating. Okay? So the center of mass of the wheel, or just the center of the wheel if you like, center of mass of the wheel, moves a distance of s, which is equal to the radius. So let's say r is the radius, capital R, times times the angle theta. Let me write it again. S is equal to r times the angle theta. Okay. So now if I want to know how fast this center mass of the wheel moves, then the speed of the center of mass is just the time derivative of s with respect to t. Let's just call that VCM, the speed of the center of mass. And now I can take this formula for s, take the derivative with respect to time. R, the radius, is not going to change. So I get VCM is equal to r times the derivative of theta, but the derivative of theta with respect to time is just omega. So the speed of the center of mass, how fast this wheel is moving, will just be equal to the radius times the angular velocity. Now, if you want to talk about the acceleration, and similarly, the acceleration of the center of mass there's a very simple formula. The acceleration of the center of mass will again just be r, the radius, times the angular acceleration. You just multiply by a factor of the radius. Okay, now then recall that there's all these formulas that you can use for the linear angular correspondence. Remember I did this in class before. We have displacement. We had, for the linear case, for the angular case, we had delta x. Over here, for the angular case, the displacement would be just the change in the angle, delta theta. For velocity, we had vx. Over here, we would just have omega. Okay, angular velocity, linear velocity. And then for the acceleration, we had ax acceleration linearly. And then we have the angular acceleration. And then we have these kinematic equations. All right, your favorites. You have things like Vx is equal to V0x plus Ax delta t. And then over here you would have omega is equal to omega naught, omega 0 plus alpha delta t. Okay. We had something like delta x is equal to 1/2 Ax delta t squared plus V0x delta t. And over on this side we would have delta theta is equal to 1/2 alpha delta t squared plus omega naught delta t. We also have vx squared minus v0x squared is equal to 2ax delta x. Hopefully all this is familiar. And then we had omega squared minus omega naught squared is equal to 2 alpha delta theta. And then just one more Vx average is equal to 1/2 V0x plus Vx, and then omega average is equal to 1/2 omega 0 plus omega. Okay. These are the analogs of linear to angular correspondences. All right, hopefully everything I wrote down is pretty familiar already. Now what we're going to do is we're going to make another connection, another angular correspondence, and it's called a moment of inertia. Moment of inertia. So the moment of inertia is all about how easy or difficult it is to rotate, to start something rotating. Okay, this is what I call the analog of mass for rotations. Right? We know that if I have an object that has very little mass, it's easy to make it move, okay, to accelerate it. But if I have an object that has a much larger mass, then it's hard for it to accelerate. The same thing about something for rotations. However, if I take a look at this pen, it's rather easy for me to rotate this pen because it doesn't have much mass. But if I were to try to rotate the pen this way, it actually turns out to be a little bit more difficult because more of the mass is sticking out away from the rotation axis. So for the moment of inertia, it's not just the mass that matters, it's actually how far away the mass is from the rotation axis. All right, so let me give you a formula for a single particle. And let's say we have some rotation axis. So we're going to try to spin this particle, make the particle go around this axis. Let's say m is the mass, and let's say the distance is r. So we're making the particle go around this axis. Okay? And the formula for the moment of inertia is capital I for inertia. The formula for a single particle is I is equal to mr squared. So it has units, it has a funny unit of kilograms times meters squared. So the further the object is from the rotation axis, the harder it is to make it rotate with a certain angular acceleration. Okay, now if I have several particles, we just add the moments of inertia together. Okay, so here's the rotation axis. Oops, off the screen. It's a bit fat. So I have here is M1 with radius R1. Let's see, over here I have something at distance R2 with M2. And then the moment of inertia, this whole thing will be M1 R1 squared plus M2 R2 squared, and so on if there are other things. If I wanted to calculate the moment of inertia of some extended object, in general, here's the rotation axis. And I have some object like this. What I would do is I break it up into pieces. And then for each piece, I figure out what is the value of Ri. Let's say it has a mass Mi. And then the moment inertia would just be the sum over all the pieces from 1 to capital N, let's say, MI/RI squared. And then I can take this as an integral. Okay. Now, it's convenient, though, to give some formulas for the moment of inertia for certain objects about their symmetry axis, so for some useful objects. So the moment of inertia about the symmetry axis for a couple simple examples that are widely used. So here are some useful formulas. The first one is for a thin hoop or a ring. Okay, so if I have a thin hoop or a ring, I have something like this. And so I have some radius capital R, and this is my symmetry axis. I'm rotating. This is rotation axis. And if the mass of the ring is capital M, then the moment of inertia is capital MR squared. It's just like the formula for a point particle at radius R. It's because you can think of breaking up the hoop into a bunch of point particles at the same distance from the rotation axis, and so they all add up with the same value of R. Okay. Now the next formula, useful formula, is a uniform solid disk with, okay, so let's just say radius M and mass, radius capital R and mass M. Now, solid disk, the same formula will work for a uniform solid cylinder. Okay. So I would have something like this, but it's actually filled this time, so this thing is actually filled in. And this is radius capital R. The formula in this case, there's a factor of 1/2. It's 1/2 MR squared. Okay. And then we can also consider the case for a uniform solid sphere with radius R and mass M. In this case, we would have like this. Okay, and it's the whole thing is filled with solid material uniformly, and the formula for this is 2/5 MR squared. All right, the last thing I want to mention is the case that sometimes we need the moment of inertia about an axis that doesn't go through the center of mass. Okay, and there's a very simple formula for that. So suppose I have, for example, we have here a moment of inertia, let's call ICM, so it goes through the center of mass. And I want to know, so that's corresponding with this rotation axis. Suppose I want to know what is the center of mass if I pivot around this rotation axis here. Okay. Instead of this one, I'm doing it from this one. If the axes are parallel, and there's a separation h between the two, and the object has a mass m, there's a very simple formula. So this is for the center of mass, moment of inertia. And this is some general moment of inertia about a parallel axis. Okay, so this is what's called the parallel axis theorem. And there's a very simple formula for the general moment of inertia about another axis that's parallel to one that goes through a center of mass. And the formula is that I, about the new axis here, this new axis that I'm highlighting here, will be equal to the moment of inertia about the center of mass through the center, through the symmetry axis, plus the mass of the object times the separation between the axes squared. Okay. So that's the formula. The moment of inertia through a new axis, this is through the new axis, that's parallel to the one that goes through the center of mass. And this is the total mass. And the h squared, the h is the separation between axes. All right, one way to motivate this formula is the moment of inertia about the new axis is actually, this formula is the moment of inertia of a particle with mass m at a distance h. So the extra piece you're adding is the moment of inertia as though all of the mass of this object was crushed down to its center of mass and it was acting like a point particle. Okay, so you take the center of mass moment of inertia about its own center, and you add the moment of inertia of a particle with all of its mass crushed down at the center, and that gives you a moment of inertia about the new axis, m squared. All right, if you have any questions about this lecture, please ask the student who's supervising today. And otherwise, I'll see you next time.